Hi, let's take a look at the new Keysight 1000X series oscilloscope, take it apart and see if we can find a debug serial port inside this thing and see what we can see. Who knows, we might be able to modify this thing, hack this thing, maybe get some extra functionality or something out of it. Let's give it a go. Now, it's very common for modern bits of test gear, especially ones that run embedded OSs like Windows CE and the like, to have a debug serial interface or like an RS-232 terminal type interface that displays boot information and stuff like that. So usually you can access this on the PCB. Now, if you're real lucky, it'll be labeled like serial interface or debug or something like that, and you're looking for things like TX and RX and like a header and things like that, but I don't think that we're going to be lucky here. Let me take the processor board off here, but if we have a look at the main board here, these are all like voltage test points, AC trigger in, voltage 1.2 volts, 1 volt. Over here there's a clock, a data, all that sort of stuff, but that's to do with like the keyboard interface. This is the USB port here. Don't know why that chip is missing there. They're obviously bypassing that. Basically, I can't see any header. There seems to be nothing on the main board here, and I've had a look at photos on the bottom side of the board because I did a teardown. There's nothing on that main board, nor would you really expect it, I guess, although there could be. But let's have a look at the processor board. So what we're looking for is an RS-232 type serial interface. It doesn't have to be RS-232 signal levels. It can easily be TTL or 5 volts, 3.3 volt, just regular digital logic. Once again, we've got JTAG here because we've got T-clock, TDO, TDI, TMS. That's all JTAG stuff. We've got another JTAG in here. So we've got these test points, and they're all labeled very nicely. We've got another JTAG down here, and we've got these debug. Now, you might think it's that, but I believe the debug has to do with the MegaZoom 4 ASIC chip that we've got here, whereas our Windows CE operating system is working inside this processor. So that's a SPEAR 600-2. So there's clearly nothing on the top side here. There's a couple of pads down in here. But if we have a look at the bottom side here, the good news is that all of the BGA pins looks like they're fanned out to an individual via on the bottom of the chip like this. It's a really quite a 400-500 pin chip or something like that. Good thing about that is they're not tented either, which means that they have no solder masks covering them, which means that we can get our multimeter probe on there, a really sharp one, and get in there and we can buzz out and measure the continuity for every single pin on that chip. Beautiful. But once again, we don't have anything, any test pads or anything like that that looks remotely like a serial port or anything to do with a serial port. So I think we're out of luck there. What's that? Is that a bug? And here we have it, the SPEAR 600, which is not recommended for new designs, apparently. So there you go. It doesn't mean that you can't get it anymore, but that's what it says on the website. Basically got a ton of stuff built in. It's got USB host, USB devices, gigabit Ethernet, I2C, synchronous serial ports, 2 UART interfaces, which was what we're interested in here. Almost certainly, because I believe we're seeing it on the 2000 and 3000X series scopes, so they're going to do the same thing here. And Keysight, for their Windows CE stuff, we have actually seen UART interfaces like this before. So it's almost certain that it's in here somewhere. UARTs, here we go. But that doesn't really tell us anything, does it? We need to find the pins. So what we're going to do is search for UART here, and let's have a look. UART pins, that's the one we want. Page 27. This is a multi-hundred page document, so you got to search for stuff. It's pretty tedious to find things, but that's the debug interface. We don't actually want this, even though I've called it like a debug type interface, and that's what it is, but it's serial terminal. So that's different to the actual ARM processor debug itself. So what we want to do is go down here to our UART. Here we go. UART1 TXD is the pin, so it's got 2. We don't know which one it is, but if we copy that and then we search for that particular pin, here we go. Ta-da! Here's our pin mapping for our, 400-500 pins or however many is on this chip. AA19 here. So AB19, AA19, they do them rows and column based with these BGA grid packages. Okay, so what we want to do, the pin mapping's usually at the end here. Here it is. Is that the one? PBGA 420. Just always make sure it only comes in, yeah, it looks like it only comes in one chip type. There you go. So 420 pin. It's a bit of a beast. But you can get over 1,000. I've used chips with over 1,000 pins. No worries. Anyway, here is the A1 ball pad corner. So that's the one that we want to find. And what was it? AA19 or something. So here is row AA up here and 19. So it's going to be up in this quadrant, opposite corner to the A1 ball pad corner. You notice how the other ones have little notches taken out of them here. And there should be like a big identifier on top of the chip. So let's find that, and then we're looking at the opposite pins over this side. There is our pin 1 dot, or our A1 dot over here. You'll notice that the notches are taken out of those corners there, but our tracks are somewhere on these pins under here, or should be. And you can see nothing coming out here. This is a 10-layer PCB, by the way, so there could be lots of traces buried in the middle that you can't see. Best guess would that it would be coming out on the connector here, because they would want to plug this board into a development test jig, and that's what this debug serial interface is for. Terminal interface is for development and, checking firmware production, checking and all sorts of stuff. So they're going to want to plug it into here, and they can access this via a bed of nails. You don't need they saved a few cents. Cents matter on this board, so they didn't need it for an actual production board, so they took it off, but they can still access those via bed of nails. So if you knew the exact pin, you could just do all the ones in that quadrant, whatever, and then just scrape along there with the continuity tester. Other way to do it is to simply probe all of these and see if you get lucky. And bingo, that didn't take long at all. I was just probing around the bottom corner of the spear chip there, and bingo, but only during the boot period is this debug serial terminal port actually spewing out boot information and stuff like that. If you wait until it boots and then probe around, you won't be able to find anything there on the board. So once again, we're searching for a 3.3 volt logic level signal on there. And just a little pro tip here, because you're probing multiple pins one after the other, and you're looking at the screen at the same time to make sure any signals are coming up, make sure you don't short out the vias, by the way. These are very close together. Even though I've got a sharp point on our scope there, you just want to be careful with that. Anyway, pro tip, put on some variable persistence like, that's infinite. Put on some variable persistence like a second or something like that. If we power that up, you'll see that, you can just, see information pop up. It just means that the information stays there on the screen a little bit longer. Okay, so a single shot captured some data there. What we want to do is go in there and just measure the baud rate. So this is where your cursors come in handy, or you can just do it manually. You just need to be in the ballpark here, so you can actually see that it's, it's serial UART type information. There we go, 115.2. Now, just be careful which point you measure here. You can see that I'm measuring one where obviously the signal is changing every bit. So we actually don't want to measure a whole cycle here. Just beware of that. We actually want to measure the period between the two pulses. So basically the one bit where it changes like that, and that'll give us our baud rate, 115K2. Okay, so what we want to go here is we want a UART RS232, and the mode, of course, is UART RS232. Set up our signals, our threshold at about a volt or whatever it is fine. We're not doing transmit, we're only doing the receive at the moment. So our bus configuration, it's almost always 8 data bits, no parity. The one stop bit, our baud rate, 115K2, and our idle mode, we're actually idling high. There, you can see that, and at least significant bit order there. So if we go in, we can now see, ta-da, does that look sensible? NAND flash. There we go, NAND flash. That looks sensible to me, you know, carriage return, line feed, stuff like that. So, you know, once you see something intelligent like that, you know, bingo, I've got myself a serial debug interface and Bob's your uncle. Fantastic. Now, I could just hold the probe on the top and capture all the information, but hey, let's solder some wires on here, and we also want a receive pin on here as well. So we want to transmit from the PC as well, potentially, to like send it commands or to interact with it perhaps. But it's useful just if you've got to receive a transmit line out of here, receive into the PC, and you can just get the dump. Anyway, it's that second via there. So if you probe in from the top, it's that one there. You can see it's a bit worn out. Done it a few times. And so we want to solder a wire onto there, and the one next to it, so the 5th pin over there, I believe is the receive pin. So that's the transmit of the PC that you're going to hook it up to. So I'll just solder 2 wires on there, and we'll be in like Flynn. Alright, so we'll just feed a bit of solder onto there and just a little bit of fresh stuff onto there as well. That's one. And that's number 2. Oh, short. I'll just tidy that up, wick that off. No worries. So the next thing you want to do is read that into a PC, and what I've got here is this nice little doodad. Because we're dealing with TTL levels here, we can't just hook it up to a regular serial port. Anyway, I've got it upside down, all the electrons are going to fall out. This is from Marlow 001.de, and I got this in the mailbag, so thank you very much for sending in. Not only does it have RS232 signal levels, but it's also got TTL levels here, and you can adjust the voltage between 5 volts or 0 and 3.3 volts. And yeah, there we go, RS232 or TTL. So we want TTL, so that just appears as a serial port. You can probably like buy a simple one that is TTL 3.3 volt compatible interface on eBay for, I don't know, $5 or $10 or something like that, but this is just a nice universal one, and we're wired up, ready to rock. And the ground point, I've just chosen the ground plane under there, easy. Okay, so what we want now on the PC is to use a terminal port program. You can use Windows Terminal or whatever it is, or you can use Termite like this. There's RealTerm, and there's many different terminal programs. It's already installed in there as COM3. The baud rate, 115, 8 data bits, 1 stop bit, no parity, 8N1 as they call it, is pretty standard stuff. So we should be ready to go. Clear the screen, and you want one that also saves the window to a text file as well. Alright, I'm going to go switch it on. Woohoo! Winner, winner! Chicken dinner! Look at this, uBoot. No, it's not U-boat, it's uBoot. Success, success, NAND flash. That's that NAND flash serial message that we captured before. And beautiful, FPGA type, it's a marsupial. Terrific. I just heard the relays click, so there we go, it's done. InfiniVision is running. As I said, it typically just does a boot dump like this. This is for debugging and setup purposes. Super valuable, essential for the developers of this, and also for doing, firmware, setup configuration hacks at the factory and stuff like that. But it can be useful for us. So there you go. I'm going to save that screen, and this will be our reference before we start doing any modifications with this thing. Now, the interesting thing here is that we don't seem to have a prompt here. Now, I'm no expert on uBoot and Windows CE, and I know bugger all, really. But I would have expected a prompt in there. And if we do something like help, for example, or help games, we get no response whatsoever. Oh, hang on. Oh. So anyway, let's look at some interesting stuff in here, shall we? There's the, it's got the Spear 600, the DRAM, the flash, everything else, Windows CE bootloader, all that sort of jazz. Fine, not found. Yeah, because we don't have a physical Ethernet PHY in there. So anyway, preparing to download, real-time clock, loading image, BL image type. By the way, this board is called the BLT board. It's got BLT on the top silkscreen copper layer. So I think that's their internal name for this processor board. So that's just like loading the image. Okay, the build here is September 28th, 2016. I have actually also dumped information from a prototype unit, which I actually have, and it shows an earlier build for this and has some changes. I've posted that over on the EEVblog forum thread, the teardown forum thread there. But anyway, so what we're going and looking for here is any sort of like configuration information, and this is interesting too. Hang on, serial 2. Okay, it looks like it's initiating that separate serial port. You remember when we saw on the data sheet for the Spear 600 that it actually had 2 serial ports. Now I've had a look around and probed it out, and I can't find a second serial port. I can't find any other serial data that's coming out at all. Here we go. We've got BLT product config 24. This is interesting. With configuration 24. I don't know what that means, but it's got different configurations, which is what we expect. And this is fantastic. Look at this, bandwidth 200 megahertz. Why? This is a 100 megahertz scope. Is the analog bandwidth actually 200 megahertz? But why has it got 200 megahertz in there? I don't know. 2 channels, of course. Board revision, FPR, whatever that is. Clock gating, Baldwin. Don't know. 4 gig samples per second. The ADC sampling at 4 gig, but 2 gig per channel, because this scope does a full 2 gig per channel, and it doesn't halve when you go down. Anyway, it's got another BLT module configuration. So there's a BLT product and a BLT module. So once again, they've got different configurations, revision LP3, whatever that means, and the sample rate, 5 gig samples a second, which the MegaZoom 4 ASIC is capable of in their high-end ones, like I think the 3000, 4000, and the 6000, whatever, they do 5, at least the high bandwidth ones, the 1 gig bandwidth ones, do 5 gig samples a second. So the chip's capable of that. Now, here's some fascinating stuff. BLT product configuration 0 and 1, ID2, ID4, and look, it's got a voltage in there, 1.246 volts, 0.692 volts, right? That's got to be volts. So that implies that they're using an ADC inside the Spear 600 to actually measure configuration resistors. Why you couldn't just use pins, like how many modes are there? Anyway, yeah, you can do that. Do it with ADCs and just set a resistor divider. So bingo, hopefully we can modify those resistor values and change the configuration. But that doesn't mean this is going to work, because I fully expect well, I know for a fact that you can upgrade the bandwidth with the license keys inside this thing, and we might be able to change the configuration, and it might say that it's, maybe if we're lucky, it'll boot up and say it's a different model or whatever. That's certainly possible. Whether or not you can actually get the serial decode option, because that requires a license as well, and also that bandwidth upgrade requires a license. So this all may be for naught, doing this hardware hacking investigation here, if you don't have the serial keys to enable those options. Anyway, that's really fascinating. So we need to take another look at the board, look for some configuration set resistors. So K9, I believe that is the main analog motherboard, so to speak. So it's measuring basically 0 volts. It's grounded there, ID 0, but we don't want to muck around. We're not too concerned with that. Now this is interesting, MSO revision. This scope does not have an MSO option, doesn't have room for it, whatever. Have they reserved that for a future release? I don't know. Anyway, that's got nothing to do with today's experiment, initializing SPGA. It's a marsupial. I love it. In June 4 to build time, June 14th. Wow. So they settled on the FPGA architecture, you know, a fair bit back. Before this, which is not surprising. You don't want to be dicking around your FPGA architecture at the last minute. If you've screwed that up, then you're in serious trouble. So factory cal stuff. There you go. That is some fascinating information in there, and it's amazing what you find when you just get these serial dumps like that, these boot dumps when you've got a complex OS like Windows CE. So let's have a look for some resistors and see if we can modify this. Do you feel lucky? Punk. This is the prototype board from my prototype unit, but it's exactly the same revision 002 here. It looks identical. If you want to know the difference between the prototype unit that I've got, I got it at the Electronics Trade Show last year. There you go. So whatever date that was, September. The processor board looks exactly the same, but the main motherboard, the K9 board, is revision 3 instead of revision 4, which I got in the production units. Anyway, so we're looking for configuration set resistors, and they're not going to be these resistor arrays here, so forget about those. There's a couple of resistors over here, but I was probing these pads over there just because they looked interesting. I got like a 30 megahertz sine wave, so it's not that. So there's no resistors on the top, so we want to be able to look for some resistors on the bottom here. There's a potential candidate, but once again, it's not going to be any of these resistor arrays. But hello, there's a whole strip. Bingo. This is what we want. Look, that looks like a resistor divider. The thicker trace there is obviously going to be ground or power, and then we've got the thin signal trace going off to a via, which then goes under here to one, you know, to some pin somewhere on the board here. So these, for all the world, look like set resistors right next to the chip. So if we flip it over, hello, we can access those. Beautiful. And I love untented vias. We don't have to get in there and scrape off. We can just probe. Thank you very much, Keysight. And the PCB layout person who went, I don't want those bloody tented vias. Can't hack and probe the thing. Bugger that. So what we want to do now is just go measuring around there with the multimeter and see if we can get pretty close to the voltages. So we're looking for around about 1.25-ish volts and, you know, around about 0.7 volts or something like that. If we can find those voltages, they're pretty specific. So I think if we can find those, I think we could be in like Flynn. Hello, 0.6 volts, and we can, check these for activity, and I have, and there's no activity, as in signal activity on the scope. 2.41, no, 0, bingo, 0.6, let's call it 0.67 volts. That's the fourth one over there, if you can see that. What do we get, 0.68 or something? I'm gonna call that near enough. It's too coincidental to have that sort of voltage, and 1.22 as opposed to 1.25. I'm going to call that near enough as well. So that's the last one on the bottom row of that, and the fourth one over. I am going to have a go at modifying those values and see what happens. Tell you what, this Mega Zoom 4 ASIC under here gets bloody hot, let me tell you. Anyway, we're looking for the fourth pin across, so that one there, so those two resistors there, is I'll just take off one of these resistors and that'll pull it to presumably either rail, and just see if it changes on boot. See if that value actually changes. If we do, we know we've got it. Bingo. And boot her up. What are we getting? What are we getting? Is it going to change? We got it. It worked. ID 2, ID 0, BLT module config. We have changed it. Bingo. It's now 0.064 volts. So this is a 64 millivolt offset there. But yep, we got it. We were able to change the configuration of that. What that means, I don't know. You'd have to experiment with all these configurations. Great. Now comes the hard work. And that little puppy is 120K, so we can put Like, you know, it'd be okay to put, say, a 100k pot in there. If you're experimenting with this, you wouldn't want to be dicking around soldering, desoldering resistor values until the cows come home. Just whack a pot in there. Geez, you can hardly make sure I don't sneeze. So obviously, if we take out that one, there are two supplies, ground and supply, and that's our voltage divider tap. We've got another one here which looks to do the same thing where the two resistors are joined, but we've got 4 channels that it's measuring the voltage from. So yeah, we've got, okay, so these two resistors and these, I'm going to assume these two as well, still need to verify, but I think, you know, it's a pretty decent bet. Why? I mean, if you were laying out the board and these were a voltage divider tap, you'd have a trace between those two, not two separate things like that. So it doesn't make sense. And we've got 6 vias along here and only 4 voltage tap points. So I don't know, does this one only go to the supply and that's it? And likewise, this one only go to the supply? The only way to find out is to suck them off one by one and note the changes. And just a little tip, if you want to get some fine wire down there, my standard 30 gauge mod wire doesn't do it, but just get a stranded bit of tin copper wire, and they're usually small enough to get down almost any via, except the, you know, the real micro ones. Now that's what I'm talking about. Here's a mod for you. Flying wires coming up. Those individual strands there, got 2 pots here. These are just super glued together, and then a little dab of super glue to hold it down on the board. Not too much, so you can actually prise it off later. It usually doesn't do any damage. And like, you could have maybe attempted to put one on this side, one on that side, and try to bend the leads over, but nah, too hard. Much better to mount them elsewhere and then route fine wires over to there like that. And it might look like they're shorted there, but they're not. They're crossing over with a fair bit of air. Awesome. And the thing about mounting them separately like that and then rigidly coupling them down to the board is that it decouples the stress from the trimmers here. So, you know, you've got to put your screwdriver in there, you push too hard, and if you've got them right on the solder joints there, it's not good. So decouple the stress. That's today's tip. So once we've installed the pots, we boot it up. The pots are still set to factory mid-level roughly, or whatever it is they are. We're getting ID3 and ID4, which is totally different to what we had before we've done the mod. And the first thing we see in the dump here is that it actually shows 0 gig samples per second for the board configuration, not the product configuration, the board configuration. But hey, if we go into here to the scope, we can show that it's actually 2 gig samples per second, and the scope is exactly the same. We haven't changed our model number or anything, but once again, we wouldn't expect it to because we're only changing that board configuration. So what that board configuration is doing, I don't really know, because it doesn't seem to make a difference in terms of the actual operation, the sample rate, because the educational model has a lower sample rate, for example. So it's just not doing it. We have to get the product ID. So it seems like the only thing that those 2 pots are going to adjust is the processor module sample rate. But what that actually means, because that's different to the product sample rate, and it doesn't seem to be affected by the sample rate when you're actually using the thing. So yeah, all those pots for just the sample rate. Bloody Murphy. And I'm feeding in a 1 volt peak-to-peak 100 megahertz sine wave here, and I've verified the 1 volts peak-to-peak on my 500 meg 3000X series scope. So it's showing about 880 millivolts peak there. So, you know, it's like it's kind of what you expect for the 100 megahertz bandwidth, because in theory, for 100 megahertz, it's going to be down by 3 dB or 0.707. So it's doing reasonably well there, actually. What I wanted to show was that it is actually doing the 2 gig samples per second, even though we've changed that, and it seems to be working just fine. So the product sample rate is just as it should be. And there you go, 0.707 at 131 megahertz or thereabouts. So it's got, you know, a fair bit better than its nominal 100 megahertz quoted bandwidth. So I've actually had some more play around with this. I've taken off a few of the resistors down the bottom there, and I cannot yet find that product ID, but it's got to be there somewhere. I just need more time, or maybe if before I get around to it, somebody else has already found it, because I'm sure there are definitely people working on this. So I have no doubt if we find that product ID, then it starts getting interesting, because that board ID doesn't seem to be doing much that I can see anyway. But it shows that we are actually getting boot changes and configuration type changes by changing some resistor values on there being read from the ADC. So I hope you found that interesting, just looking at like a systematic procedure, how to find a serial boot UART in a product like this, and being able to get some useful info and like start the process of hacking this thing. But as I said, it's probably going to require license keys and everything else to really get, you know, say the embedded options and the extra bandwidth and stuff like that. Anyway, that's all we got for today. I'm sure there might be more parts on this if we can get more information. So if you like that video, please give it a big thumbs up. Thumbs up, it fits on the screen. There we go. And as always, link down below to the EEVblog forum to discuss, where people are discussing hacking this baby. Catch you next time.